Okay, so hello everyone. A very good evening. Welcome to today's live interactive session. So, in the previous week, we studied some of the basic concepts of reinforced soil walls, and in today's week, we will be actually uh, continuing that topic and then actually dealing with how to actually check the stability. Okay, to how do we actually check the stability of these reinforced soil walls? Those things we will be studying, and then we will be solving some two or three problems regarding some of the concepts that we study. Okay, so let us start. Right. So the first thing that we have is the external stability analysis. Right. So in the external stability analysis, what we do, we check the factor of safety of our structure in terms of the lateral sliding, the overturning, the bearing capacity failure, and the overall failure. And the overall failure. Right. So lateral sliding means what? So we have our reinforced soil wall. Okay. We have our reinforced soil structure, and so on that some horizontal forces are acting. So one horizontal force is due to the earth pressure of the soil, right? One is that, and one you can say one of the horizontal forces that are acting, that is the earthquake forces. The other horizontal force that is acting is the horizontal force due to the crash barrier. Say you have a pavement that is constructed over the reinforced soil wall. So due to the horizontal force that might come when a vehicle collides on the crash barrier, so that is one, right? So these are the horizontal forces that might come. So these horizontal forces actually might cause our structure to slide. Okay, slide over the foundation soil. So you need to check whether this sliding, whether this sliding is prevented by the friction that occurs between the reinforced the soil block and the foundation soil. All right. So that is the lateral sliding. And then we have the overturning check, where see, due to all the loads, there is a overturning movement, so there is a chance that the structure will actually rotate about the heel. Okay, rotate about the heel, or it will rotate, it will overturn. So we need to check that, we need to ensure that there is no such overturning failure, right? Then the third is the bearing capacity failure. Bearing capacity failure means the foundation soil above which we have constructed the reinforced soil, this reinforced soil structure, that foundation should be strong enough to hold that reinforced structure. Okay, so there should not be any this bearing capacity failure, or there should not be any excessive settlement. Yeah. So these two things we should check. And the third is the overall failure. So in the overall failure or the slip circle failure, this generally it tends to get neglected. Okay, but it is very important that we check the overall failure of the structure, so that uh, this slips are, so say you're constructing this RE wall over some slope. Okay, so you need to ensure that the slope over which this structure is constructed is safe. Okay, there is no failure of the main embankment slope. Main slip circuit, where slip circuit failure is not there. All right. So these are the stability checks that we do, right? Now, now from this, what we do from this, what we need to ensure that the length of the reinforced soil block that we consider, that reinforced soil block actually satisfies all these criteria. And during all this calculation, this reinforced soil blocks is considered rigid. Okay, during all these stability checks, what we do, we consider that these reinforced soil blocks are rigid. It's a rigid structure. Okay, so after that we have the embedment depth. So embedment depth is nothing but how much this foundation should go inside the soil ground level. Okay, it is nothing but the embedment. So certain criteria are given by the this Federal Highway Administration. So it is given here. Okay, now the first thing, as I said, is the check for lateral sliding. That is the we need to determine the factor of safety against sliding. Okay, so we have our reinforced soil wall. In that we will have this reinforced soil block, right, which we considered as a rigid structure. Okay, we have the reinforced soil wall. Then in that reinforced soil wall, this backfill soil, okay, this backfill soil is going to give some lateral earth pressure, right? It's going to give some earth pressure laterally, it's going to push it. And also there are going to be some surcharge loads. Okay, so we are going to construct some road over it, so the weight of the dead load of the pavement, then the dead load of this crash barrier and other things, those things will contribute to this permanent surcharge. And then you have, say you have a highway constructed, so the road constructed, so the vehicles will be moving there, right? So there is, so you need to provide for the live load surcharge. Okay, this live load will be considering this vehicular load. Okay, vehicular load, whatever other live loads that might come. Okay, so due to these surcharges also, what will happen, they will also cause some lateral earth pressure on the reinforcer, right? And fourthly, this pH is nothing but the horizontal load at the crest due to the crash period load. So say we have a pavement, and when there is a vehicular crash, what it collides with the crash period. So during that condition, what happens? It exerts a lateral force, outward lateral force. Okay, so our construction should be such that this everything should be this crash barrier should actually hold the structure in place, right? We should not let the this contribute to the movement of the complete wall. So we need to consider that load also, right? So you can see this total horizontal, this lateral load that is coming on the reinforced wheel. It is nothing but the earth pressure due to this backfill soil. Then we have the earth pressure due to this surcharge loading, and the lateral load from the crash beacon, right? And these lateral loads should be actually prevented by the shear resistance that is developed at the base. Okay, so shear resistance, how to get the shear resistance? Nothing, normal load multiplied by the friction, this mu. Okay, this mu, this friction ratio, right? This normal loads multiplied by the this friction ratio is similar to mu is the friction ratio between this reinforced soil field and this foundation soil. So some foundation soil is there, right? So that gives the accounts for the friction mu times the vertical loads that is coming. That is nothing but gamma into h into L, that is from the reinforced soil field, and QD into L is from the surcharges. Okay, and then what we do, then we can determine the factor of safety. It is a resisting force divided by sliding force, and generally it should be greater than 1.5. Okay, now now say we have this back-to-back walls, right? So generally this is the most common scenario when we construct this reinforced soil walls for say some highway. So this is the most common scenario, right, for highway approaches. So we have a approach where two sides we need to construct this back-to-back walls, isn't it? So in back-to-back walls, what we need to account for is that this overlap distance. So for this wall we have this Rankine's active wedge, okay, and from this wall also we have this Rankine's active wedge. So what we need to consider is the overlap distance. This overlap distance d, where this where to uh, this Rankine wedges, active wedges actually intersect. Alright. So if the overlap distance is about 0.3 h, where h is the height of our wall, then what we do, this k we can take as 0. This is a lateral earth pressure, we can take it as 0. Okay, so sliding jack is actually not required in that case. And if the two blocks are away, okay, then what we need to do, we need to take k is equal to 0. All right, and if this overlap distance is less than 0.33h, then what we do, then we just interpolate the value of k between 0 and k. All right, so see, so this part up to here, yeah, yeah, that's okay. All right, okay. Now let us see what's there next. So next we have the factor of safety against overturning, right? So due uh, so please give the solution of questions 15. For this is for the solutions, please ask. I don't have the solutions. All right. So you can just ask the course TS if they have the solution, because they are correcting your assignment and everything. So what we can do is that you can just write your query in the discussion forum. Okay, in the course discussion forum, you can write, and actually the course TAs will handle your queries regarding the assignment, because they are forming the questions and they are solving. Okay, still I will see next week. I will see what are questions 14 and 15 of week 4 assignment 2. Okay, I will see that. And week 4 assignment to see tomorrow. I think tomorrow you are about to submit your week 4 assignment, right? So anyways, I cannot discuss the solution now. After tomorrow only, you can, what you do, you can, if you are unable to, if you want the solution, what you can do is you can write in the discussion forum. Okay, discussion forum of the course, and the course TAs will probably handle this. Okay. Okay, and next week, see, and even though if you do not get the solution, what I will try to see what the questions are, and I will try to solve from my side, and I will try to give you the solution in the next week. All right. So this overturning moment, what I was saying is that, so you are having a reinforced earth wall, right? And there are some loads, lateral loads acting on it. So due to these lateral loads, there will be some overturning moment, right? So overturning moment about this heel. So there is a tendency for the whole structure to rotate. Right? So that is nothing but the overturning moment. So similarly, in that you can see the same contributing loads are there. First is due to the backfill earth pressure due to the backfill swell. Then we have that due to the live this surcharges due to the live load and the dead load, and the other is a moment due to the crash period. All right, and here also what another thing that you can add is that the lateral force due to the this seismic loading. All right, that will also come into picture. Okay, and what will be the resisting load? The resisting load is nothing but the weight of the resisting moment will be contributed by the weight of the structure, the weight of the soil mass, right? So, okay, so the weight of the soil mass, that will be actually contributing to the resisting moment. So you have this, say this is the length of the reinforced mass, right? So this weight will be acting at L by 2, L by 2. So this downward vertical load will be actually resisting this overturning moment, right? And also you can see this QD, whatever dead load is that is there, that weight will also resist this moment. And one more thing you should notice here is that the live load is actually neglected in this resisting moment calculation. Okay, so generally we don't consider the live load in this while we calculate the resisting forces or resisting moment. Okay, here also you can see in the shear resistance we did not consider the live load. Here also we are not considering the live load, only the real. Okay, same. This factor of safety against overturning. Similarly, resisting moment by overturning moment, it should be greater than 2. Okay. Now the third thing is the bearing capacity check. So bearing capacity check, what we do first, what we need to determine is the load. Okay, the vertical pressure that is coming on the foundation soil, right? So same loads will be contributing here. What are the vertical loads? First load is the weight of the soil mass, right? The weight of the soil mass, and then the weight of the surcharges due to the dead load and the live load, right? Plus any other permanent loads. So that is contributing to the vertical flow. Now after that, what we do, we determine the eccentricity. So eccentricity means what? Say this is the this is the reinforced soil. Okay, this is the base. So total vertical, some vertical load is acting. So this is the center of the base. So generally what happens, this vertical loads actually act at some eccentricity from the center of the foundation. So that eccentricity is nothing but the resisting moment, sorry, the overturning moment divided by the load. So that will give you the eccentricity, and we need to ensure that this eccentricity is actually less than b by 6 in soils and less than b by 4 in rocks. So can you tell me why are we checking for this eccentricity? Why should this eccentricity be less than b by 6 and less than b by 4 in rocks? So generally it's less than b by 6 only. So can you tell me why is eccentricity less than b by 6? What is the reason? Why do you need to check for this eccentricity? Why do you need to actually check? Huh? In columns we considered it. Columns. You're talking about RCC columns. What is the need for eccentricity check? Okay. So here these vertical loads will be acting at some eccentricity, right? Yeah. So why do you actually need to check for this eccentricity? Just think while we discuss this. Just think about why do we have to check for the eccentricity. So this we have studied this thing uh, in from starting from our basic this mechanics of solids or the strength of materials topic. From there we have start we know this thing. From there then we again studied this in basic soil mechanics. So you should be able to answer why do you need to check for this eccentricity. Okay, just think about it. Okay, so what we do, we determine this eccentricity, and then we determine the bearing pressure on the foundation soil is nothing but RB divided by V minus DC. Okay, so that will give the bearing pressure on the foundation soil, and this bearing pressure should be actually less than the allowable this bearing capacity of the soil. Okay, so this bearing pressure should be less than the allowable bearing capacity of the soil. All right. So, can someone define what is allowable bearing capacity? What do you mean by allowable bearing capacity? What is meant by allowable bearing capacity? How do you determine the allowable bearing capacity? So generally what we do is that first we determine the, yeah, one is settlement. Okay, so one is the settlement criteria and other one is the bearing capacity criteria. Okay, so these two criteria we should consider, right? So first what we do, first we determine the bearing capacity, this net ultimate bearing capacity, and then what we consider is that we calculate the pressure that is coming from the permissible settlement. So lesser of these two we take as the allowable bearing pressure. Okay, allowable bearing capacity. Okay, and this bearing pressure that comes on the foundation shell should actually be lesser than the allowable bearing capacity. Okay. Now, types of bearing capacity failure, you know, this first is a general shear failure, then we have the local shear failure, then another one is the we have the punching shear failure. So generally for soils having phi greater than 36 degree, there we have general shear failure. So in general shear failure, this there is proper formation of the this failure wedges. Okay, and then we have the local shear failure. Okay, for phi values approximately between 20 to 36 degree, and then we have the punching shear failure. So for very weak soils we have the punching shear failures where these failure surfaces actually do not develop at all. Okay, and how to estimate the bearing capacity? This bearing capacity estimation is done following the IS 6403. So you will be solving one problem where you will be using IS 6403. Okay, and yeah, and the other thing that we were talking about is the, so bearing capacity, the first we determine the bearing capacity from here, and then for the ultimate settlement we can check for this here settlement check. So how you can do the settlement check? We need to calculate the settlement. So first is the immediate settlement, then we have the consolidation settlement. So consolidation settlement, as you all know, is from the primary and secondary consolidation settlement, and the secondary consolidation settlement mostly occurs in organic clays. Okay. Yeah. Now let us come to that question again. Why do you do this eccentricity check? So see, if this eccentricity is actually greater than b by 6, what will happen is that the pressure, this generally the pressure distribution is something like this. Okay, this pressure distribution at the base is something like this. So what will happen if this eccentricity is less than b by 6, then sorry, is greater than b by 6. So what happens is that there is a tendency for this tensile forces to actually come into play. And as you all know, soil is actually weak in tension, right? Soil cannot take tension. So we should prevent that. When that so that is the reason what we do. We need to check for this eccentricity so that all the forces below the all the pressure that is coming below the foundation, that is actually compressive in nature. Okay, that is why we do the this eccentricity check. And yeah, and the last check that we need to do is the this overall failure check, where what we do, we check in this slip circle below. So first thing what we do, we need to identify the this slip circle. Okay, where the this failure tendency of the failure will be maximum. Okay, we need to identify this failure wedge, and then what we need to do, we need to take this, find out this factor of safety. So in the factor of safety, you can see the numerator is that is the resisting. Okay, this is the resisting. These are the resisting moments. So from where are these resisting moments coming? So you see, this is the slip circle, right? So in the slip circle, what we do, say the soil tends to slide downwards, right? So there will be there is development of this shear forces at the interface. So these shear forces actually prevent the failure slipping of this failure, prevent the failure of the soil, isn't it? So the in the above the numerator is nothing but this resisting this moment of this resisting shear force. The first component, it is from the cohesion of the soil, C into LA. LA is nothing but the length of the slip surface. Okay, so C is the cohesion of the soil, La is the length of the slip surface. Then comes tan phi into Wy cos alpha is nothing but this resisting force that comes from the weight of this. So this, so what you are doing, you are dividing this into some small wedges. Okay, and then what you are doing, due to this weight of each wedge, there is some resisting this weight. So one component will be acting downwards, so this is downwards, so one is component is acting downwards, and one component is acting like that. So this one component will be actually preventing the slipping of the this uh, slipping of the soil. So this is the contribution of the weight of the soil mass, right? So first is the contribution of the cohesion of the soil, second is the contribution of the weight of the soil, and third is the contribution of the reinforcement. So you are putting some reinforcement, so you are reinforcing the slopes, say, with some geosynthetic material. Okay, you are reinforcing the soil with some geosynthetic material. All right, so what will happen is that, so due to the reinforcement, there will be some this tensile, due to the tensile, due to this reinforcement, tension and the reinforcement actually prevent the slipping of the surface, right? So that you are considering here, that is the T. This T actually comes from the reinforcement, right? So the numerator forms our resisting moment and below resisting moment or resisting forces. Okay, this is force by force, not moment. Resisting force by this causing disturbing force. Okay, they're force by force. And you know, in the denominator we have nothing but this component, sine component of the weight, that is nothing, that is causing the sliding of the, that is the disturbing force. Okay, that is what is causing the slope to fail. Okay, this is nothing but the other component of the weight. So one component of the weight, you can see, this is the normal force. So this is the normal force. Let me draw it here. Say this is one wedge. Okay, so this is the weight that is acting here. So one component of the weight will be acting like that, and other component of the weight is acting like that. All right, so this component of the weight, this is nothing but Wy sine alpha. Okay, this is actually causing the failure. Okay, causing the sliding. And other force is the shear force. The shear force is nothing but what? tan tan phi means the friction. Okay, the friction, this friction coefficient into the normal force. The normal force is nothing but the cos component of the weight. This is nothing but Wy cos alpha I into this tan phi. Okay, that will give the component of the shear resistance. Okay, understood? That is from the weight. Another is the cohesion. The cohesion of the soil will also actually prevent the failure. So that is from the cohesion. Okay, and the third is the third comes from the reinforcement. So these are the three components that are preventing the failure, and this is the causing the failure. This is nothing but this. This is nothing but Wy sine I. Okay, so we'll be solving some problems later on in more detail. All right. Okay, so then we have the seismic loads. So as we know, this IS 1893 actually defines all how these seismic loads are to be considered, right? So the latest version is, I guess, to the IS 1893 2016. So first we have this base acceleration factor. This base acceleration factor consists of some parts. So first is the this zone factor is nothing but Z. Okay, so India is divided into several zones, and so based on the probability of occurrence of earthquakes. All right, so this Z is actually Z actually defines the this zone factor. All right, and see, you can see here for four zones India has been divided, so from 2 to zone 5. Right, for zone 2 the zone factor is 0.10, and for zone 5 the zone factor is actually 0.66. All right, that means very severe. All right, and then we have this importance factor. This importance factor is nothing but how important our structure is, that defines the importance factor, right? That is also given in the IS 1893. After that, we have this SA by G. SA by G is nothing but the spectral acceleration, right? So you will have some period of our structure, right? So that structure you will have some fundamental period, and corresponding to that period, what we can do is that we can determine the spectral acceleration coefficient SA by G from this graph, which is shown here. Okay, so from there what we can do, we can determine the spectral acceleration coefficient from this graph, and you can see for different types of soil, so that structure, so generally this is given for buildings, right? So say the building is located on rocks, so you can see we have one spectral acceleration coefficient, like one graph, and for medium soil we have one graph, and for soft soil we have one graph. So it depends on what type of ground, on what type of condition soil our structure is situated. All right. Okay. From there, what we, so we determine the period of the structure, and from there, what we determine the spectral acceleration coefficient. Okay, that will give the SA by G factor. And the third is the response reduction factor. So this response reduction factor is nothing but, say your structure is very rigid, then this response reduction factor will be low, right? And say your structure is very flexible, then this response reduction factor will be high. All right, so flexible structures less effective earthquake, right? So that's why, so for flexible structures we are having higher response reduction factor. Okay, so from that what we do, we determine this base acceleration factor. Okay, we determine this base acceleration factor, and from this base acceleration factor what we can do, we can determine the average acceleration coefficient in the soil, that is alpha m, using this relation given by the Federal Highway Administration. Okay, so first we determine alpha, and that alpha you can use here to determine the average acceleration coefficient in the soil. Okay, okay, here is the this seismic zonation map of India. So you can see our entire northeast region is actually in this zone 5, and this Gujarat region, if you remember this Bhuj earthquake, okay, and this regularly earthquakes are uh, occurring in our northeastern region. Okay, such few days back, I suddenly got a call from call from home saying that there is earthquake. Okay, so regularly in northeastern region earthquakes keep on occurring. So that's why this has been given in zone 5. And you can see the other regions also are divided into these four zones. Recently, I heard that like they are considering up to zone 6 in India. Okay, so they are increasing the number of zones up to zone 6. Okay, so let us see when that comes into this application. How to calculate tensile force transmitted to particular reinforcement layer. Okay, this ten you are asking how to calculate tensile force, how to transmitted to particular reinforcement. So that these things actually we will see in detail. Okay, while we do the designing of reinforced soil hulls. Okay, we will be solving detailed problems where we will be like this determining the length, the embedment length, all those things. So what we need to do is see the main our main task, what is our main task? Our main task is to determine the length of the reinforcement, right? So that will be first the length inside the failure wedge and then the embedment length. So to determine all these lengths and the spacing of the reinforcement, what we need to do, we need to determine this force transmitted. Okay, the force transmitted in all this is one of this reinforcement here. So there is nothing but this para this say you are using some geotextile. Okay, generally what I can remember is that, so in general, how to calculate, what we do is that first we take the vertical pressure, that vertical pressure times the uh, friction coefficient, that will give you the this shear force that is developed, this force that is developed on the reinforcement there. Okay, we will see later on how in detail how we can calculate that. Okay, we will see, we will solve some problems also, if not today in the net class. I think in week 5 sir has actually taught those things. All right, so we will be seeing that slowly one by one. Don't worry, we will be solving detailed problems. We will be seeing how to determine this reinforcer, this how to determine how to design a complete reinforcer one. Okay. Okay, so then, so here nothing, here it is just detailed how we can determine the seismic loads. So in this determination of seismic loads, similar to previous cases, what we do determine the, we consider the reinforced block and the backfill block as two separate entities, right? We consider them as two separate entities, and from there what we can do, first what we do, first we determine the influence of the backfill, this backfill block on the reinforced block. Okay, so due to the earthquake, what will happen, in the force, the inertial force of the backfill block will be affecting the reinforced soil block, so that we consider by this PAE. Okay, that is given by this, and the point of application is also given. And then we have the inertial force of the reinforced block itself. Okay? So that is given by this. So then after that what we do, we sum both of these. So we assume that the peak values of both of them are not, obviously not going to reach the peak at the same time. So that is for some uh, optimum design, we consider that, so that the cost of this cost of the construction can be optimized. So we, this is so we make this assumption that both of them are not going to reach the peak at the same time, and so we take 50% of this AE, and then we take 100% of PIR. We sum both of these to get the total seismic force. Okay, so this is the total seismic force that is actually added to the other static forces that we discussed just previously. Now there is a static forces from the earth pressure, the static forces from the crash barrier, the static force from the surcharges. So all these things, it should be added to that, to actually added to that, and then consider, and all of these should be actually considered together in the external stability calculations. Okay. Okay, this Mononobe Okabe method is nothing but a generalized method given by Mononobe and Okabe to determine the uh, seismic load. Okay, the seismic load that comes into play for any, in case of any retaining wall. So here we consider retaining wall having some angle alpha and generalized backfill soil inclined at beta. So in that case, what we do, how we can determine this. Uh, Determine this is a seismic coefficient, and how you can determine the seismic load was actually given by Mononobe. Okay, this was actually one of the uh, first research papers that gave this method to determine the seismic loads. Okay, they used this is nothing. This is other name of this is the cytostatic approach. So they use the cytostatic approach to determine the uh, horizontal and vertical horizontal component of the earthquake, and how that actually influences the loads, okay, the seismic loads. Okay, so as I said, the total forces are the sum of the seismic forces, And the other static forces means that is the self-weight, surcharge load, crash variance, etc. Okay. And when we include the seismic forces, what we can do, we can reduce the criteria for factor of safety by 75%. So say in general the factor of safety criteria for sliding was 1.5, but if we use this seismic forces, what we can do, we can reduce that by 75%. So our factor of safety can be 1.125. Okay, should be greater than 1.125, right? So after that, we have the internal stability analysis. So in the internal stability analysis, so we discussed this in detail, right, in the initial lectures. So what actually influences the internal stability is nothing but the rupture, pull out, and third is the connection failure, okay, or the excessive movement of the facing. So rupture, we already discussed. What is rupture? Rupture means the force that is acting on each of the reinforcement is actually exceeding the tensile strength or the allowable tensile strength or the tensile strength of the reinforcement. In that case, what will happen? The oncoming load into the reinforcement is actually exceeding the strength of the reinforcement, right? The allowable tensile strength that is exceeding the tensile strength of the reinforcement. In that case, that the rupture of the reinforcement will occur. All right, and the other case is the pull out failure. In the pull out failure, what happens? There is loss of friction between the reinforcement layer and the soil. So what happens if there is loss of friction? Say this is the reinforcement layer and this is the soil. So if there is loss of friction between the reinforcement and the soil, what will happen? This reinforcement will slide out, right? It will get pulled out of the soil. It will get pulled out of the soil mass. That is nothing but the pull out failure. Okay, so these are the two most important failure types of failure. One is the rupture failure and other is the pull out failure. When does rupture failure occur? Rupture failure occurs when the oncoming load into the reinforcement actually exceeds the tensile strength of the reinforcement. In that case, the reinforcement cannot take more load, obviously, and that's why it ruptures. It breaks, it snaps. Another one is the pull out failure. When does pull out failure occurs? Pull out failure occurs when there is loss of friction. There is loss of friction and resistance between the soil and the reinforcement layer. Okay, so when load acts on the when the so when loads acts on the reinforcement, there is frictional, okay, frictional resistance, there is mobilization of frictional resistance, right, at the interface. This frictional resistance, what happens? This prevents this sliding of the reinforcement. But what happens? What if this force exceeds the limit? So if the force exceeds the this shear limit of shearing resistance, what will happen? It will slide out, right? So there is nothing but the pull out failure. And the third is the connection failure or excessive movement of the facing. That means what? Connection failure means the reinforcement actually connected to our facing, right? We discussed how they are actually joined to the facing blocks or all those modular blocks. We discussed all those things, isn't it? So those are connected to the facing. So connection failure means was there is loss of connection between the reinforcement and the facing block. So what might happen? This facing this connection might break. That might be one case, or the other case might be that there is excessive movement of the facing one. So in both those cases, both of them, if in case of excessive movement of the facing or in case of the complete failure of the connection, we consider that it has failed or structure has failed. So all of these three will contribute to the internal stability. So we need to consider that there is no rupture failure, there is no there is no chance of pull out failure, and there is no chance of connection failure. There is no chance of excessive movement of the facing. Okay, so what will happen? Say this is the connection and this is the reinforcement. Okay, these are completely tied to each other. So if the connection suddenly breaks, what will happen? This will fall outwards, right? There will be excessive movement of this. There will be excessive movement of this movement of this facing outwards, because see, earth pressure is acting like that, right? So continuously there is tension on the reinforcement. So if this joint breaks, obviously it will, there is going to be excessive movement of the this facing, right? So we need to check for, we need to prevent it. Just a Okay, so forces in each reinforcement layer, right? So as you were asking, so how to calculate the lateral forces? So from where is this force actually coming? Okay, this tensile force, it is coming on the tensile load, it is coming onto each reinforcement. From where is it coming? So say you have say this is the, say you have this reinforcement like this, right? So in each of the reinforcement, one is what? One is the weight of the soil that is acting, right? So nothing but the self weight of the soil. Then say, sorry, say you have uniform surcharge at the top. So due to that uniform surcharge, also one downward force is acting on the reinforcement, right? Then you have the then other one is this bridge abutment load. Okay, so say you are constructing this reinforced soil wall here. In this case, in that case, some extra load we need to consider, that is nothing but the this bridge abutment, right? Then fourthly, we have the horizontal load, this in the backfield due to traction. So traction means what? Say at the top you have this railway tracks, right? The railway tracks or something, some movement is there. So due to that, what happens? That is traction on the surface. So that tractional force also causes some load on the reinforcement. That some of that load is also considered reinforcement. So that we also need to consider. Then the crash barrier load, as we all discussed, and the last one is the inertial force to the earthquake. So all these loads are actually acting on this reinforcement here. Okay, so we need to calculate, we need to consider all of these loads while we calculate the load on all this or load on the reinforcement here. All right. Now here it is described how to actually calculate the bridge abutment load. So we have some vertical load that is coming from the bridge deck, and the other part is the this load due to this part. Okay, this pavement load and the load due to the backfill. So what we do actually, to get the equivalent vertical force on the wall, what we do, we deduct the load due to this backfill. This gamma into h will give the load of this backfill, plus ws will give the load of this pavement, into b, that this part we actually deduct from the vertical load coming at, okay, from the bridge deck, just to get an average load. All right, just to get an average load, what we do, we deduct this from p to get the equivalent load pq, and that load we actually consider as the vertical load on the wall. All right. Yeah, now horizontal loads affects only the reinforcement layers that fall inside the active wedge draws from the, okay, so say uh, say you have a footing, all right, placed over a reinforced soil wall. So it is said that the loads that affect the reinforcement layer are the loads only falling in this region. Okay, the loads falling within this region will be actually will be actually affecting the reinforcement there. So say we are designing a reinforced soil well, in that case we have some foundation over it. Okay, foundation over it. In that case, when we calculate the vertical loads on each reinforcement layer, we need to consider this criteria. Okay, so we need to consider this criteria while calculating the vertical loads. All right, so that is just given here. This tz is nothing but this horizontal force it is coming. So this is the foundation. In that foundation some load fh is acting, and this tz actually gives the distribution of this fh into this reinforcement layer with height. So with variation of z, it gives, say we have a reinforcement at depth z, so it is giving the horizontal force that is coming on that reinforcement at depth z. Okay, so this fh is actually distributed like that. So you have fh that is acting on the foundation, horizontal force that is acting on some foundation. All right, and that fh is actually distributed on this reinforcement layers. How is that fh distributed? This is distributed in this way. Okay, so at depth z, this is the tensile force that is distributed from fh. Okay, the part of fh that is transferred to the reinforcement layer at depth z. All right, b is the width of this footing. Okay, width of this footing, this is b. D is the distance of the center of the footing from the wall. B is the width of the footing. These are like, see, now what we are discussing all the loads that we should consider for the internal stability. Internal stability check means this pull out check, tensile failure check, and that this what this excessive connection failure check. So what we need to do for checking all those things, to check for rupture, pull out, and this connection failure, to check for these three things, what we need to do, we need to determine the load that is coming on each reinforcement, right? To check for all those things, the first thing what we need to do is that we need to determine the load that is coming into the reinforcement, right? So what we are doing, we are just discussing that thing, how we in different scenarios how we can determine the load that is coming into the reinforcement. So the basic loads that the soil weight, we know we can easily calculate. The low uniform surcharge, that contribution easily we can calculate. All right, so bridge abutment load, how to calculate that is given here, right? Then this say you have this fh acting on a foundation, that how to, in that scenario how to calculate, that we just saw here. So we are just seeing different cases where from where we can calculate the load that is coming on each reinforcement. Okay, and why are we doing that? We are doing that because we need to determine the force in each reinforcement layer. Why we need to determine the force in each reinforcement layer? To check for the internal stability. And what is our internal stability? Check for rupture, pull out, and this connection failure. Okay, and one more thing, if you notice here, is this TA. This is the allowable design strength. Okay, say you do a, say you have a geogrid and you do the tensile testing of the geogrid. From there, what you will get? From there, you will get the T ultimate, the ultimate tensile strength. Now, this ultimate tensile test that you have just done, that is under optimum lab conditions, right? You got some sample from the factory, and like in the safe environment, in a closed controlled environment, you are using the test, right? But in practical cases, that environment, there are n number of factors that affect the strength of the reinforcement, right? That might be the some environmental factors, right? Environmental factors, say this chemical effect of the soil. So chemicals might be present in the soil, that might affect the reinforcement, right? That might affect the polymer of the reinforcement, that might affect the strength. Then this while placing you might while placing the reinforcement in the site, okay, in the field, you might damage the reinforcement, isn't it? You might damage the reinforcement, that might affect the strength, isn't it? Then there will be creep. So creep means what? Creep means constant, under a constant load, deformations under constant load, right? So that will be affecting the strength of the tensile strength of the reinforcement. All right. So all these extra things, all these extra effects that are out of our control, okay, because we have to do the construction in the field, so that is a no, it is not a controlled environment, right? That is an uncontrolled environment, isn't it? That environment is uncontrolled. There are n number of factors that are affecting, but when you are testing in the lab, it is a perfectly controlled environment, isn't it? So what we need to do, we need to consider these factors, consider these various factors in order to reduce the ultimate tensile strength. So what we do in our calculations, we consider this allowable tensile strength for a conservative and safer design. Okay, so say if we consider this ultimate strength in your design, what you will do? There might be this, say, while construction, there is damage. Okay, so you are assuming that in the field also I will get ultimate strength, but in reality, what happens? Because of the damage, you are not getting this ultimate strength, and due to that, our structure may fail, structure may collapse. So what we need to do is that we need to consider all these factors. We need to, in order to consider all these factors, we use certain these reduction factors. Okay, so here, so actually corner is, corner actually gave this TAS T ultimate divided by three factors, that is the R chemical biological R creep, and this R, this construction damage. Okay, these three he gave. Okay, so this was given by corner. Okay, now now comes, okay, now comes the thing where now someone had asked that how to calculate the tensile force transmitted to particular layer, and this is the answer of that. Okay, this answers our question. So how to calculate the force transmitted to the reinforcement layer? This is what, so as I had said, is nothing but the vertical force into the friction coefficient, okay, into the this spacing will actually give you the force transmitted in each reinforcement layer. Okay, so say this is the reinforcement, and we consider that this is the total spacing, right? So we consider that the soil SY2 above and SY2 below actually affects the soil. It actually affects the soil. So what we do, we consider this spacing, this SB here. Okay, so the vertical load multiplied by KF into SV. Okay, vertical load, so actually vertical load into, this is, say, this is, now say it will be in kilonewton per meter square, right? Into, this will be in meters, this spacing, and this will be in, this will have no unit, this is some coefficient. Okay, this is how we are actually converting the vertical loads into the horizontal loads. All right, so this will be in kilonewton per meter. So every calculation is per meter length of the wall. All right. Okay, now here the next thing is the lateral, this lateral earth pressure coefficient. So lateral earth pressure coefficient. So generally, if the structure is flexible, what will happen? So to mobilize the active earth pressure, there might be little flexibility. There should be little deformation in the wall. So if the structure is flexible enough to allow little deformation, in that case, what we do, we consider this K as K. Okay, and for inextensible reinforcement, where the reinforcement are very rigid but do not allow any movement, in that case the earth pressure is little bit high, and we consider this earth pressure at rest, cannot. All right, and there are some many criteria given on how to consider that, so that is given here. Now comes this important part is the this force that we are talking about, right? How to calculate this force in reinforcement? The force in reinforcement at any depth z is given by the spacing times the earth pressure coefficient in the soil times the vertical pressure that is coming. Okay, so that gives the force in each reinforcement. So say you need to determine the force in this reinforcement, so you determine the vertical pressure that is coming into that reinforcement times the earth pressure coefficient times the spacing. That will give the force in each reinforcement. So the force in reinforcement at each depth should be actually less than this allowable tensile strength, right? So that will be actually less than the allowable tensile strength. So this force should be less than Ta. Else what will happen? If it is greater than Ta, then rupture will happen, right? So we cannot allow rupture to occur. So this force that occurs should be actually less than Ta. All right, then yeah. Eh, And here see a very important thing is written, and you can see from here also this vertical spacing actually reduces with depth. Obvious reason, because as depth increases, the vertical pressure is increasing. The vertical pressure is increasing. The vertical pressure is increasing. The force in reinforcement also will increase. So in account for that, what we do, we reduce the spacing of the reinforcement. All right. Now embedment length. So embedment length means the length that you have to provide beyond the failure wedge. So it is the most important thing, right? The embedment length is what that holds the reinforcement in place. So here providing the reinforcement here. So this is the active wedge. This is the active wedge rupture plane, and you are, so this is the reinforcement, and beyond this beyond the active wedge you need to provide some extra length. So this extra length gives some anchorage to the reinforcement. Okay, so the minimum recommended this length embedment length is 1 meter. So minimum 1 meter of embedment length should be provided. So this embedment length actually gives allows for the anchorage, allows the reinforcement to hold the reinforcement to that in place. All right. So this embedment length is actually very much important. If this embedment length is not given, what will happen? The Due to the forces that are coming to the reinforcement will just slide out. All right. So there will be pull out failure. So prevent pull out failure. This embedment length is very important. Okay, we have to provide this embedment. Now, first, we already studied how to check for rupture. We will we will solve problems, right? Don't worry. As we progress in the course, we will be designing reinforced soil walls. Okay, they ourselves. We will see how to design, how to calculate all these things, how to calculate the force and reinforcement in the. We will be seeing all these things. Okay, there is no hurry. That is what I mean. So do not, there is no need to hurry. Ample amount of time is there. So as time progresses, we will be actually seeing how to calculate. So in that you will see how we are checking for all those things. At that time it will be more clear. You will get more clarity on that. So the force coming on some reinforcement. So what we do, we need to ensure that that is like less than the allowable tensile strength. That is the rupture check. And now next what we need to do, we need to check for the pull out. Okay, so the pull out check, what we need to do? So force in the reinforcement. So force in reinforcement. This force in reinforcement should be less than TA. That is the allowable tensile strength. That is our rupture check. Okay. Now this force in reinforcement should also be less than the pull-out resistance. This is the pull-out check. Sorry, the pull-out check. So this should also be less than the pull-out resistance. Now, how to determine the pull-out resistance? Pull-out resistance is nothing but the vertical load times the friction coefficient, that will give the frictional force, frictional pressure, frictional resistance times the length, that will give the pull-out resistance. So this sigma b is nothing but the vertical force that is coming at any level. Okay, let's say the vertical force that is coming here, it is given by sigma b times alpha 10r. So alpha 10r is nothing but similar to mu. It is the friction coefficient. Alpha 10r, alpha 10 phi r is nothing but the friction coefficient. Okay, the friction coefficient between the reinforcement and the soil. Alpha 10 phi r is nothing but the friction coefficient between the reinforcement and the soil. All right. So this friction coefficient times the vertical load, that will give the frictional force times 2, because 2 surfaces, times L, that will give the frictional force, total frictional force per unit length. That should be actually less than the uh, this, sorry, you should actually greater, right? Sorry. No, less only. Yeah. So that should actually be this PR, this pull out resistance should be actually greater than the load that is coming to the reinforcement. If the load is greater than this pull out resistance, what will happen? It will just slide out. The reinforcement will get slide out. So this resistance should be higher than the load that is coming to the reinforcement. So this factor of safety should be greater than 1.5. So this LE is nothing but this length. This length is LE. LE is nothing but L minus this part. So do you know this angle? From there you got this. So L minus this part will give you this is L. So L minus this will give you LE. Okay. This is what is written here. Now testing requirement. So we studied many things, right? So we need to determine the various forces, and these various forces, some are coming from the soil, from other things, all these things. So then some properties are so info. So for that, what we need to do, we need some soil properties, some reinforcement properties, some reinforcement interaction factors. Okay, those things we need. So first is the soil property. Soil property means what is the friction angle of the soil. This is the most important thing that we need to know. Then comes the reinforcement property. So what is the reinforcement property? Reinforcement property is nothing but tensile, allowable tensile strength of the reinforcement, that we need to know. Third is the soil reinforcement interaction factor. That is nothing but the friction coefficient between the soil and the reinforcement. This thing we need to know, this alpha. So that is the soil reinforcement interaction factor. And third is the reinforcement facing connection, that is the strength. Okay, the how the reinforcement and the facing is interacting. So all these things we need to determine by various tests. So soil properties, friction angle can be determined by direct shear test, that is the shear box test. Generally weak friction angle is used. The next thing that I said is the reinforcement property is nothing but the this long term allowable design strength, the allowable design strength given by this. Okay, so that is conducted by wide width test or narrow width test. Many type of tests are there, right? Many types of tests are there. So with those tests we determine this allowable tensile strength. Okay. Okay, so here you see here we use various factors, right, to reduce the ultimate tensile strength to the allowable factor. So we have some installation damage, creep, chemical biological demand, joint seam strength, all these things. So installation damage also we have to test. For all these things, what to determine all these factors, what we need to do, we need to do certain different tests. Okay, so let us see how this let us see one video how this creep testing is actually done. All right, so just share the screen. Just a second. So this is the video for creep testing. Okay, so this is the load cell that is used to give the constant loading onto the geosynthetic. Then we have this LVDT here that measures the strain. It measures the strain or the displacement in the reinforcement. Okay, so that is actually placed inside this closed chamber, and this closed chamber is actually thermally controlled, heat controlled, and this is actually the video is actually about the accelerated tensile creep test. So generally, you know that creep test actually take long time, right, many years, but so we generally do not have that much time, right, to do the test. So what we do in order to accelerate this test, we use this method where we do the test at various temperatures. So you see this closed chamber, inside this closed chamber this test is happening, and this chamber is actually thermally controlled, heat controlled. Okay, this load is applying at the top, load is applied, tensile load is applied, and we have this LVDT inside and measures the displacement. And here you can see this is actually the blower, thermal blower. This maintains the temperature inside. So at intervals of 12 to 15 degrees, what we do, we consider you do this creep test, and then these test results, what we can do, we can extrapolate these test results to get the creep behavior at any amount of time. All right, so in that way, this way we actually do this accelerated creep testing. Okay, then we have the installation damage test. So in the installation damage test, what we do, we first we do that in the field only. What we do, we place a steel plate, we place aggregate, we place the geogrid or the reinforcement, then we place the again we place the cover aggregate, then we compact it. After that, what we do, we pull the specimen out of that place. We pull out we take out the geogrid from that place, and we test that specimen. So what we do, we test both the virgin samples and the exhumed sample. Exhumed samples means that we put on the ground, right? We could take both of them out, and then we do the testing, and we compare the results, and from there we determine this installation damage factor. Okay, and after that we have the connection test. So connection test is nothing but we apply some load. Okay, so this reinforcement is connected to this block, this facing block, and then what we do, we apply some load here. So due to this load application, as a point will come where this connection will break, so we determine that point of failure. And then we have the pull out test. In the pull out test, what we do, we put the reinforcement between the soil, and we apply some load, pull out load, and as we increase the load, a point will come when the reinforcement will completely come out. Okay, Okay, that will give the peak pull out load. Okay, it will give the peak pull out load. So here you can see at various vertical pressures. Various vertical pressures, obviously this peak pull out load is going to be different, right? Right. So we find out this peak pull out load P, and then from this relation, what we can do, we can determine this interface friction angle. This interface friction angle is nothing but the friction angle between the reinforcement and the soil. This delta you can determine, and from this delta, then we can determine this alpha that we need to use. Okay, so you can. So let us see one video for this. See, so this is a geogrid. Okay, so what this is simple test. What they are doing is they will be pulling that with hand. Okay, just to test. So this is the geogrid that they are testing. First, what you will do, they will be testing a geomembrane. Okay, this is the geomembrane load cell pulling device. Okay, this is the geomembrane, and this is the this testing box. First, we put the material, the base material, level it. After leveling, what we will do, we will compact it. After compaction, we place the geomembrane. Then we will again put the fill material. Okay, then we put some normal pressure. So these two people setting here, they are actually generating the normal stress. Then what we do? Then we start pulling. So we pull, keep on pulling, keep on pulling, pulling, pulling. If you will reach a peak load, and then we'll keep on reducing. Okay. Now let us see the test for the geogrid. See, high strength is required. Okay. So we keep on pulling it. It reaches a very high peak. Okay, but still it does not feel. They are unable to pull with that strength, that much strength. Okay. But still the geogrid doesn't feel. Now this way actually this pull-out test is done. Obviously this geogrid will be having high pull-out resistance because of the force, because of the apertures. See, this is the for the geomembrane, this is for the geogrid, right? So obviously this geogrid will be having just tap. Why is it not visible? Yeah. So as I was saying, obviously geogrid will be having higher this higher pull out resistance because there are pores so due to that big aperture size, what happens, there is interlocking between the soil and the geogrid. All right, so higher strength is actually needed. Now this is the test for the anchored this is the relation for the anchored reinforcement. Okay, so now just now let us try to solve some problems. Okay, let us try to solve some easy problems. Okay, just a second. Yeah, so the first problem is calculate the factor of safety in sliding using FHWA method for a 10-meter high reinforced soil wall. Friction angle of soil is 35 degrees and unit weight is 18 kilonewton per meter. Friction angle of foundation soil is 30 degrees. The width of reinforced block is 7 meter. Permanent surcharge is 10 kilonewton per meter square and live load surcharge is 5 kilonewton per meter square. The maximum possible load in crash barrier is 25 kilonewton. So what we need to do, first we need to calculate the factor of safety in sliding. Okay, so to determine the factor of safety in sliding, we need to determine the total horizontal loads that are acting. Next, we need to determine the total horizontal loads that are acting. So the first horizontal load that is acting is due to the earth pressure, is due to the backfill soil, earth pressure of the backfill soil. Second is that from the surcharges of the dead load and live load. Then we have this load from the crash area. So if you sum all of this, you will get the horizontal load that is active. Right? So let us calculate that. So let us first write the expression for P. So P is horizontal load P is half Ka square AP plus BH. Alright. Now for that what we need to do, we need to determine KAB, right? So what is KAB? 1 minus sine phi. So 1 minus done. So we got KB. So now what we can do, we can easily calculate speed. Half height is 10. What is pH? 25. Right. So please calculate this. Let us see how much this one is coming. P is sum of all these three. So the first component is from the earth pressure of the backfill soil, half kb. So we have this triangular distribution, right? So this is this first part. And the second is our pick from the surcharge. Yes. So the first one, if we add it will be, please check this, okay, by your check the calculation might not be correct. Please check the calculation from your end. Done. So this is the disturbing horizontal force, right? Now what is the resisting horizontal force? This is nothing but the friction that is developed at the base between the reinforced soil block and between the foundation soil, right? So you need to determine the shear resistance. So shear resistance equal to mu times friction coefficient times the vertical load, gamma into h into L plus qt into L. Okay, so live load, as we discussed, while we calculate the resisting forces, we do not consider the effect of live load, right? So what is mu? Mu is nothing but the friction coefficient between the foundation soil and the reinforced soil block. How to determine mu? Mu is nothing but 10 times 2/3 of phi. And which is this phi? This phi is the lesser one between the phi of foundation soil and the phi of the reinforced block. So our question, it is given that the foundation soil is a phi of 30 degrees. Okay, therefore we have 10 by 3 into 30. So this will be 0.36 to 0.36 times 18 into 10 into 7. L is nothing but the length of the reinforced soil block. It is given as 7 meter. Width of the reinforced soil block. So will come out as 478. Therefore, factor of safety is on sliding, but 478 meet 305 546 greater than 1.5. So it is safe in sliding. Right? Now, for the same case, what we need to do, we need to calculate the factor of safety against overturning. Okay. Remember that in all these cases, you're neglecting the seismic load because it asks in the question to neglect. But in generally in the field, what we do, we need to consider the seismic load also. Just for simplification here, we are not solving, remaining that for the seismic load. For the same previous scenario, calculate the factor of safety against overturning. So for that, what we do, we determine the overturning moment. This is the overturning moments 1/6 kb gamma hq by 2 kb. All right. So this part is from the earth pressure of the backfill on the reinforced soil wall. This is earth pressure of the surcharges due to live load and dead load, and this is the moment due to the what? Due to the load in the crash wheel. Ten plus five square plus 25 into 10. So if we add all this will be 813 plus 203.25 plus 250. Okay. After that, what we need to do? We need to calculate the resisting moment. So the resisting moment is given by what? Given by the weight of the soil mass. Resisting moment is the weight of the soil mass and the weight of the this dead load. Dead load surcharge, that will be actually weight of the dead, this is the dead load, and the weight of the soil mass, that will be actually contributing to the resisting moment. So let us calculate that. So this will be 465. So what is the factor of safety against overturning? Is greater than 2, hence safe. Alright. Okay. Now let us come to the next one. Calculate the net ultimate bearing capacity of a strip footing of width 5 meters situated 1 meter below the ground level. Soil is dry, having unit weight 18 Newton per meter cube. Friction angle 36 degree. Cohesion is 5 kPa. And water table is situated at a great depth. Consider general shear failure. Alright, so friction angle is around 36 degrees, so we can consider general shear failure. So you have a strip footing. It is located 1 meter depth below the ground level. The width is 5 meters. So what we need to do, we need to determine the bearing capacity, net ultimate bearing capacity of the strip footing. So what we will do, we will sort to IS 6403. Okay, so let us just see IS 6403. So you can see, in case of general shear failure, the net ultimate bearing capacity is given by this expression. Right, is given by this particular expression. So this expression, what are the terms? CNC, SCDC, IC plus Q NQ minus 1 SQ DQ IQ plus half B gamma N gamma S gamma D gamma I gamma and W dash. So C is nothing but the cohesion. NC is the bearing capacity. NC, NQ and N gamma, these are the bearing capacity factors. And the bearing capacity factors are related to the 5-degree angle of friction, and that we can get from this table. Alright. Then we have SC, SD and Is. SD and Is are nothing but the S is nothing but the shape factor. Okay, and for strip footing, these are all 1. Right? Then we have the depth factor. That is nothing but these D's. Okay, for D's we have this depth factor. And I is nothing but the inclination factor. Means if the load is applied at some inclination, that accounts for that. So in our case, this will be 1 only, okay? Because our load is completely vertical, there is no inclination, so I's will be 1. I's will be 1, S's will be 1. These D's we need to determine. Okay, so these D's we need to determine, and this you can see for our soil as phi is 36 degree, right? But this here we have 35, then directly we have 40. So what we will do, we linearly interpolate between 35 and 40 to get this NC, NQ and N gamma for 36 degrees. Okay, so first, so I have already done the interpolation, linear interpolation. I will just keep the results for you. So what we do, so for 36 degree, this NC actually comes out as around 51. Okay, 51.96. This NQ comes out as 34.98, and this N gamma comes out as 60.31. Okay, so N gamma comes out as 60.31 for 36 degree. So this, how did we get this? We will just linearly interpolate it between 35 and 40. We will get the value for 30 degrees. Alright. So let me just write that down. Phi is equal to 36 degree. 36 degree we have, and check these values yourselves, okay? Once, don't just rely blindly. This calculation, there might be mistake. I might have done some mistakes. So check yourself. And if there is any mistake, please feel free to tell. Okay, the NC, NQ, N gamma we got. Now we need to determine. So SS will be 1, I will be 1. We determine DC, DQ, and D gamma. Alright, so what is DC? 1 plus 0.2 df by v root over n plus n. 1 plus 2 df by v and 5. Okay, this is DC depth factor. Okay, so 1 plus 0.2 into df is how much? Depth is 1 meter by 5, and root over nq. What is root over nq? What is root over nq? Sorry, n5. What is root over n5? What is root over n5? N5 is nothing but our this root of this active earth pressure coefficient. Just a second. Just I will confirm this one. Okay, myself I have forgotten. Just a second. Yeah. So n5 is 10 square 45 plus 5 by 2. It's nothing but Kp. The passive earth pressure, not the active. The passive earth pressure coefficient. Okay. So root over n5 means 1045 plus 5/2. So let us determine this DC plus 0.2 5 1045 plus what is 536 degree 1.08. Okay, this is 1.08, and other thing that we need to determine is the dq is equal to d gamma. What is that? dq is d gamma 1 plus 0.1 df by 1 plus 0.1 1.04. Okay, so close to 1, values are close to 1 only. Okay, so now what we can do, now we can determine this q net ultimate. So q net ultimate CNC SCDCIC C is 5 kPa into NC. What is NC? 51.96 into DC, it's 1.08 plus Q. What is Q? Q is nothing but this overburden. 1 into 18. This 1 into 18. It's 18, right? So 18 is NQ. NQ is 39.48 minus 1. DQ is 1.04. It's half 18, 5, 60.31 into 1.04 into what is W dash? See, if say you have a foundation, depth of the foundation is DF and this is B. If water table, this is B, lies below this depth, below if water table lies below DF by B, then this W dash will be 1. If it lies between DF and DF plus V, then you interpolate between 0.5 and 1. And if it water table lies above this DF, means here or say here, okay, then it will be 0.5. Okay, this is how this W dash varies. So it is given in the IS code. See, if the water table is likely to permanently remain at lowered below a depth of DF plus V beneath the ground level, then W dash is 1. If the water table is located at the DF or likely to rise to the base of the footing, then it's 0.5. And if it's between DF and DF plus B at any distance dW, then it will be interpolated between 0.5 and 1. Okay, that means it say it is at this here. Then you can interpolate it. Now let us just calculate this one. 5 into 550, 1.96 at 1.08. Okay, 3823.44. So we got Q value. So this is the net ultimate bearing capacity. Now next calculate the bearing pressure on the foundation soil for the scenarios given in problem 1, calculate the FOS in bearing if the foundation soil friction angle is 30° and question is 20 kP. Okay, so for our first problem, now we need to calculate the factor of safety in bearing. Okay, the friction angle of foundation soil is 30 degrees, right, and question is 20 kP. All right, so see, first if we remember what we need to do, first let us determine the loads that are coming onto the foundation, right, the vertical pressure that is coming. So for that, first what we will do, we determine the vertical load RV, starting by gamma HB plus QL plus D to B. So we have 18 into 10 into B, 7. B is the width of the reinforced soil block, right? 7 plus 10 plus 5 into 7. So we have 1365 kilonewton. Got RV. Now let us calculate this eccentricity, nothing but MO by RB. So if you remember, moment resistance, resisting moment was this overturning moment was 1266.25 divided by 1365. This will give you 0.93. So whether it is less than B by 6, so what is B? B is 7 by 6, that is 7 by 6, 1.167, so less than B by 6. So okay, right. Now let us calculate this vertical pressure, 1365 by B minus 2IC. So 1365, 7 minus 2 into 0.93. So 1365 divided by 7 minus 2 into 0.93 to 265.56 kilonewton per meter square. All right. Now this is the vertical pressure that is coming. Now what we need to do, now we need to calculate the bearing capacity of the soil, allowable bearing capacity of the soil. So the base soil is 30 degrees, having 530 degrees, so it is less than 36 degree. So and between greater than 28 degrees, so we will have local shear failure. Now in local shear failure, what to do, we to determine this bearing capacity factors NC, NQ and gamma. We first of all we reduce this phi by 2/3. Okay, we determine phi dash is equal to tan inverse of 0.67 tan of 30. So this will give us tan inverse of 0.67 times is 2/3 of tan 30 is 21.15 degrees. Now corresponding to this 21.15 degrees, we should determine this NC and Q in form. So it's given here for obtaining values NC dash and Q dash and gamma dash, calculate phi dash equal to tan inverse 0.67 tan phi. These dash values are for local shear failure. Okay, we see here we have dash values, right? So in case of local shear failure. Now again, this 21.15 value is not available, so what we can do, we can interpolate between 20 and 25 to get this NC and Q and gamma. So I will just write these down. Just check all these values by yourselves. Okay, so NC dash equal to 60.18, NQ dash 7.38, dash is 6.65. Done. Now this we need to determine this D depth factors, DC 1 plus 0.2 df by b root over n phi Where is it? Here, right? 1 plus 0.2 df by root over n5 and dq gamma is for 5 greater than 30 10 degrees. But what is our depth of foundation in this case? See, this reinforced soil wall, what we are considering, see, it is like this constructed, right? And this is the foundation. This is the foundation soil. This is constructed. So, sorry. Okay. So, yeah. So, this is the foundation soil, right? What's wrong with this? Yeah. So this is the foundation soil. So so you are considering that this thing is the footing, right? So footing is just placed over the ground level. It is not at some depth. So in that case, our df will become 0. So all these things will actually become 0. So this is also equal to dq d gamma. So as df is 0 in our case, so dq and d gamma will also be 0. Alright, because the depth of foundation will be 0 in this case, because we are considering that it's just lying over the ground surface, over the foundation. Alright, now let us calculate the net ultimate. C and C, everything is 1, rest is 1, plus Q and Q minus 1 into 1 plus of gamma B and gamma into 1. No water table also, so we can relax. So what is C? C is 20 into NC is 16.18. What will be Q? Q is what? Q is gamma into df, right? But df is 0 in our case, so Q will be 0. So it is 0 plus half. Gamma is 15. B7 6.6. Calculate 20 into four one five 742.5. Now this is the net ultimate bearing capacity from what? From this bearing, just directly the bearing capacity, right? Now actually what we need to do, we need to also determine the settlement. Okay, you took to the test, and from that settlement, from allowable settlement, actually we get what? This allowable bearing pressure. But when we have no, we don't have this settlement rate. So what we do, we just take a factor of safety. Allowable will be nothing but nu by 3. So that will actually, this factor of safety around 3 actually takes into consideration like of the this settlement factor also. If we take the factor of safety 3, so you can take allowable as knu by 3. So 2.55 divided by 3 will be how much? 742.5 divided by 3 is 247.52 kilometer per meter square. So what will be our factor of safety? 247.5 by 265, which is actually less than 1.5. So not safe. So in this case, that foundation is actually this. In this case, our structure is actually not safe against this bearing failure. So bearing failure is chance of occurrence of bearing failure. All right. Now, next we have this: calculate the allowable tensile strength for a geotextile with ultimate tensile strength 200 kN per meter to be used for slope stabilization. So this is actually given by Corner in his book, this Designing with Geosynthetics. In that book, it is given. All right. In that book, he represented this allowable tensile strength. Okay, this allowable tensile strength is T ultimate by some reduction factor. Reduction factor, one is the installation damage, one is the creep, another is the chemical biological damage. Only these three factors. Okay, this is given by Corner, Robert M. Corner, in his book Designing with Geosynthetics. So this T ultimate is 200. Now it is told to us to find out for how much, for the geotextile to be used for slope stabilization. So here, from here you can see, for slope stabilization or installation damage, reduction factor is 1.1 to 1.1, 1.5. So let us take 1.5. For creep it is 2 to 3, so let us take say 3 only. And for chemical biological damage is 1 to 1.5, so let us 5. So if you do this, you will get the allowable strength. Allowable tensile strength is 6.2. All right. So that was all for today. So with this we end today's session. So actually, see, there are not much problems to solve in this case. No? Like these problems I have to formulate by myself. There are no in books also, generally from these parts there are no problems, are not there. Okay, and good problems are actually given in your assignment questions. So try to solve those problems by yourself. The assignment questions, there are some good problems. You can solve those by yourself. And so mean the problems we will be starting to solve from this designing part, where we will start to design. You will be designing reinforced soil walls. We will be using geotextile to be used as filter materials. So all these things we will be actually solving some problems. So that is mostly the problematic part. Okay, now whatever we are doing is mostly the theoretical part, so very less basic problems only. Now I am not getting also problems anywhere in any books so that I can solve for it. So these problems are just formulated. I just formulated by myself some problems. So and solved it. Okay. So mostly these are theoretical part. Okay, the basic concepts are actually discussed. So that is all. That is what these 4 weeks were all about, right? So in next week, let us see what we can do. If it is theoretical, if it mostly theoretical, then we will do something like that only. And if we start designing problems, we'll start to solve those design problems. All right. So design problems will take little bit more time to solve. Okay, there will be some big problems generally. So this reinforced wall problems are a little bit bigger, and the other problems, this filter and all these problems are easy and not that big. Okay, just you need to remember the criteria and solve the problem. So we will do all those things. So that's why, means what I was doing is that, yeah, I was actually more focusing on revising the concepts in all these sessions. What I was doing is that initially I was trying to discuss all the concepts and then just solving one or two or three basic problems, because all these parts, these things do not have, they are not that problematic. All this just the concepts are discussed, right? So in later, as the course progresses, what we will do is that we will see that the problem solving will take more time. Okay, so we will be giving more weightage to problem solving, and just in half an hour we will try to discuss the this theory part, and then 1.5 hour we will be solving the problem. Okay, so we will be doing that in the upcoming lectures when we go more into the problem solving part, the designing part. Now it's all basic, so there is not much. All right. And these are not this subject is not like this basic soil mechanics or foundation design and all, where there are a large number of problems available in textbooks or wherever. Okay, large. So this is very specialized and niche topic, right? So not many numbers of problems are also not available in all books. So whatever problems are available, these are all formulated by myself only, and we're trying to solve it. Even these assignment problems, those were also formulated long back. okay, by themselves only, by the TS. These are already repeated year after year, because there is no question bank from where we can say solve say 10 15 problems. Okay, so we will just more keep in this course, we will just focus more on the concepts, and then we will be solving some problems. So most important part is the designing part. We will be that will be coming in the upcoming weeks, and we'll be solving detailed problems regarding the designing part, and that will take some time also. This reinforced soil earth wall design takes some time to solve. So this we will be doing that. And then what I suggest is that you also solve, we like together we can solve that, so that will be like helpful to you. And if I just keep on solving by myself, that is of no use, right? So if you solve together with pen and paper, if you also sit with calculator, pen and paper, then things will like coincide, like you will be able to remember the steps, because those designing problems are a little bit lengthy, reinforced artful designing problems. And then after reinforced artwall or finishing, I guess we will be discussing some designing problems where geotextiles are used as say barriers or some filter material, all these things, all those problems also it will be seen. Okay, so with this, let us end the today's session. And if there is any question, you can contact me anytime. All right. So thank you for attending and have a very good evening. Thank you.